let's take a look at 8.2 on integration by parts. This is a integration technique that you will use throughout your math career. Comes up a bit, and you'll need to recognize the form to apply it. So we often just call it parts or a parts situation. So we will get right into the application. Here's the theorem, how it's done. Don't really need to go over the details of the proof or anything. So if u and v are functions of x and have continuous derivatives then, so that hypothesis basically is guaranteeing that it's integrable and stuff like that. So then the integral of u dv is equal to u times v minus the integral of v du. So in some ways, you're changing the form of it from this form to the next form, and you still have an integral. So when you apply this technique, like, you're not done. You need to continue to integrate that. So the whole idea is when you choose u and v, and I'll show you how this works, and you get this form, then what we look at is it's kind of like reducing it to a form that's more easily integrable. So this should be more easily integrable than this, or impossible otherwise. All right, so let's look at some examples. So find the integral or indefinite integral of x cubed ln x dx. And so what you do is you choose your u and your dv. You differentiate one and you integrate the other. So this is how it works. So and I'm just going to show you this time. We can discuss maybe what you choose later and all that. But let's let u equal the ln x and the dv equal the rest, which would be, it's always whatever else, x cubed dx. And then what you do is you differentiate that just like before, but you integrate this. So du is equal to 1 over x dx. And when you integrate that, you get v is equal to 1/4 x to the 4th. And you don't have the dv or dx in there anymore, you just leave it. And so now you take all of these parts, that's why it's called integration by parts, and you substitute into this form here. So this would equal, so let's just say this, I'll just recopy it. So this equals u times v, so you just put in u times your v. So that would be your ln x, so it's ln x, we'll put in parentheses. So that's your u times your v, 1/4 x to the 4th, minus the integral of v du. So your v is 1/4 x to the 4th, and then du. What is du? Times 1 over x dx. Okay, so let me just, might as well highlight since I can. So here's your your u is here. And then your v is here. Oops, I just highlighted the wrong thing, didn't I? I was highlighting that. And here's your v, and then integral of your v, which is here. Let me use the same color there. And so here it is. And then your du. So your du is this, which is 1 over x dx. I'm not sure that helped or not, but I like to highlight things when I can to show you. It looks pretty anyway. All right, so then that simplifies a bit. That's usually we'll write this as 1/4 x to the 4th, and then ln x, a little better form, of course, minus, and then bring out the 1/4 integral, and that's just x cubed dx, which clearly this is a lot easier to integrate now. That's pretty simple. So we get equal to 1/4 x to the 4th ln x minus, and then you add 1 and divide, so that'll be a 1/4 times, and that's 1 over 4 x to the 4th, and then plus c, of course. So you end up with 1/16. So it's equal to 1/4 x to the 4th ln x minus 1/16 x to the 4th plus c. So that's the parts idea. You have integration in there. It's broken up into parts. That's the concept. And so I have some guidelines down. I don't know how good they are. I'll write them down because they are in the book or some book. But this is the general guidelines, but it's worth a discussion. So guidelines. I mean, so basically you want to choose stuff to make it more simple. Not always effective, but so here's one. So number 1, choose dv to be the most complicated and integrable. So it's like complicated, but you can integrate it. It's like choose u, or in other words, u is what's left over, is what is left. So this is like an either or. So or you choose u so that du is more simple. Now, in practice, you don't have to choose the right one right away. If when you do this, and you got to be able to integrate your choice of dv, okay? Whatever dv is, make sure you can integrate it. If you can't integrate it, then you got to choose something else, but you can. Then the whole idea is once you put it into the right form, that second integral you can integrate. Right? So that's what you're after. So let's look at another one. Let's look at this example here. Do I have enough room for this? Let's just, I don't know. I might move everything down. So evaluate the integral of ln x over x squared dx. So your choice of d, so this is similar to the one above, really. But if you chose your integral of ln, that's going to be more difficult, right? I mean, you want to choose your dv to something you can integrate like nicely, not more complicated. Don't make it more complicated. The derivative of natural log is easy, right? It's 1 over x, but the integral isn't. Okay, so excuse me. So let's choose u to be ln x. And then my dv, let's have that ln x, or 1 over x dx. And I'm going to fix my messed up notes here. Can we move this over a little bit? Make it more concise. And then my dv will be that. So it'll be, let's just do that 1 over x squared, which is, we can integrate that, no problem. Okay, so try this now with the rest of it. Okay, so let's do it then. So du is equal to 1 over x dx. And my v is equal to, what is that? When you integrate that, you have x to the 2, which is negative 2, add 1 to subtract, right? So you get a negative 1 over x dx. No, not dx, I'm sorry, just 1 over x, right? Okay, so now substitute back in. And what do we have? So you have this integral here. And let's integrate back in, or put in your parts formula. So this is something you would definitely want to memorize, like the basic form. And then usually in a regular situation in classes, you'd write that down on a note card if you're allowed one. But that's something you need to know, and and remember and recognize some of these forms as you go, as you practice a bunch of them. You'll start recognizing that's a parts situation. So you get u, so negative 1 over x ln x minus the integral of negative 1 over x times 1 over x dx. Substituting all the parts in, which is equal to, now I'll just simplify, negative ln x over x minus 1 over x plus c. And that's it. I mean, this is, I didn't show you all those little steps. This is 1 over x squared, which we just did, right? It's almost like a reduction formula. Sometimes we call these reduction formulas. So you reduce this from a squared down to that, and then separated it. It's not quite the right terminology, but it's kind of what it feels like. Okay, so just to recap here, this becomes a plus, but you ended up with 1 over x, or x to the negative 2, and when you integrated that, it became that. So that's the same as we did right here with this integral, right? This is what you got. It's like you did that same integral twice. All right, so then we can simplify this. Negative ln x plus 1 all over x plus c. Okay, so I won't do a bunch of these in the videos. You should practice these. We can work on them in office hours or whatever is convenient for you, with the problem sessions. But now I want to show you the next situation that may occur. The next situation might look like this. Let's look at this example. So evaluate the integral of e to the x cosine x dx. So something like this, and I'm going to move everything over. Give myself some room to choose stuff. So when you do this, let's pick our, so we want to pick our u and our dv. So it's hard to say which one's more complicated. That doesn't really help us. And we can integrate both pretty easily. But usually you want to integrate something that's going to like change it. So so I would say this is probably the most complicated one to integrate. And then it'll be something we can work with. All right, so let's do that. So let's pick u to be e to the x, and then my dv is cosine x dx. Then we know my du is e to the x dx. That's pretty straightforward. And then my v, the integral antiderivative of cosine is sine. So let's just sine x. All right, so now let's substitute in. And we have, this is equal to e to the x sine x minus the integral of e to the x sine x dx. Okay. Now, well, this is looking kind of similar to this. So let's do that again. So let's pick our u to be e to the x, our dv to be sine x dx. Our du is e to the x dx, as expected. And then our v will be negative. So our v will be minus cosine x. So this, let's substitute into that, which is another integral. Okay, so we'll look at this. So that is e to the x and then negative cosine x minus the integral of negative cosine x e to the x dx. Okay, now wait a minute. Aren't we back to where we started? Let me simplify this a little bit. So that's negative e to the x cosine x, and then plus the integral of e to the x cosine x dx. But this is the same as what we started with. So you can essentially solve, for what we started with. So what we have then is you can say this equals all of that minus all of that. And what you're going to end up with is two of these. So you're going to end up with basically this twice when you solve for it. Okay, so let me show you what you end up with. So we get the top thing. So the given equation or expression is the integral of e to the x cosine x dx equal to e to the x sine x, but then that's minus all of this, negative e to the x cosine x plus the integral of e to the x cosine x dx. So let's go ahead and distribute that. That's equal to e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. So again, we are going to take this and isolate it. So you add it on both sides, and you get 2 times the integral of e to the x cosine x dx equal to, and then what's left, e to the x sine x plus e to the x cosine x. Divide by 2, and we have solved for our integrals. So it's equal to, or equivalent to, I should say, if and only if, e to the x cosine x dx is equal to, and you could write it as like a half or something, e to the x sine x plus e to the x cosine x plus c. So we have just solved for it. It's a little strange, right? I mean, it's you're not explicitly solving for it, but it has to be true the way we get this back. So it's like repetitive, and you get this back, and then you solve for it. So this integral equals this. Okay, I should mention there, you may have learned or seen somewhere, or it may come up, someone wants to show you a special way of doing integration by parts, and that's fine. I don't really care. I've never learned any other method, and there's really no reason for it. Speed is really not an issue to do these. They're just, there's other ways of doing it. But really, it's the form to recognize in the beginning that you want to know. It's this form that's most important, that it's a by parts situation. That, like, there's going to be a U and a dV. They call it like tabular method or something. I'm not really sure. I've never really done it. So you may use it, just don't mess it up. But if you know one method, this method, it'll something you can use for the rest of your math career. And I'm not sure it works for this case, actually, for this situation. I always ask this question on the exam, or not this one, but something very similar. So you show how to solve it. You see this repeating, and then you solve. This is a very typical one we always like to put on. And I'm not sure it works for that. I don't really know. But anyway, just thought I'd mention that about other methods. Okay, so a lot to practice on this. There's a lot of integrals posted you can do or look up, and practice these integration techniques.